probably don't know who I am. I'm Murray Rudman. I recently retired from the Department of Mechanical and Aerospace Engineer, and indeed Rosemary has taken my suggestion that it's not a bad thing to do. I'm going to talk about, if I can get this to work, okay, I'm going to talk about some work that I did at CSIRO actually quite a number of years ago, and I spent much of my career in CSIRO. I've only been here at Monash for about 12 years. I need to acknowledge a bunch of people who worked on this. Guy Metcalf, he's ex-CSIRO, he's actually ex-Monash as well. He was in the Department of Mathematics for a couple of years, or School of Mathematics. He now describes himself as a gentleman scientist. Means he doesn't get paid. And what I'm going to talk about today, which is something called the rotated arc mixer, it's his brilliant idea. I also need to mention Daniel Lester, who did some great work here, ex-CSIRO, now at RMIT. Michelle Spaetjens, who ex-CSIRO, now at Technical University at Eindhoven. I think you can see that there's a bit of a familiar motif coming out here. All these people are ex-CSIRO, including myself. But first of all, I have to mention Rosemary. Today is all about her. I've known Rosemary since 1985, I think. She's been a very dear friend over, that's nearly 40 years. She's been with us for a long time. And this is Department of Applied Mathematics and around about 1987, and in case you can't see Rosemary, she's right in the middle of everything, which is exactly where you'd expect her to be. And just in case that image isn't quite clear enough, there's another one that I took in around about 1987. That's your office. That's your office with all of these weird sort of... Yeah, indeed. Okay, so Rosemary's been with us for a long time, but so has mixing fluids. And this is a woodcut from about 1556. Rosemary hasn't been here quite as long as that. But we can see, for those of you who have any knowledge of chemical engineering, a set of continuously stirred tank reactors. You can see various different kinds of impellers here. So people have been trying to mix fluids for a real purpose for a very long time.
They look like torture instruments.
Well, they could be that as well. Mixing is kind of like, it's really obvious. We do it every day. Make a cup of tea, put in some milk, whatever it is. But the basic underlying idea of how mixing works is not necessarily well understood. So the basic idea is you take something you want to mix, for example, that red blob there, you stretch it out, you fold it up, you stretch it out, you fold it up, and you keep on doing this until the striation or the thicknesses of those inhomogeneities get so small that molecular diffusion has a chance to operate rapidly. So if you can use advection to mix things up, then diffusion can eventually take hold. If we just left the red blob there to mix, it could take hours, days, weeks, depending on what we're trying to do. So, if you know anything about fluid mechanics, you'll say, how do we want to mix? Are we going to mix in a turbulent flow or in a laminar flow? And on the example on the left there, it's a pipe flow. The colours represent the speed of fluid moving into the page. And the velocity vectors, which aren't super clear here, tell you what's happening in that plane. And so this is a three-dimensional flow, but we're visualising it in 2D. Turbulence is great. It mixes really well. You can see that it's inherently chaotic. You don't have to do anything special in a turbulent flow. The problem is we were interested in mixing highly viscous fluids. And if you want to try and get turbulence with high viscosity, you've got to put in a lot of energy. The shear rates can be very high. You generate a lot of heat, and often it's simply not possible to do. So that then leaves the alternative, laminar flow. Now, laminar flow, by and large, is entirely predictable and it's deterministic. You can tell at every point in the fluid for all time what's happening. But if you just take a standard, steady laminar flow, it's not going to do any mixing at all. It's really hopeless. Things just mix linearly in time, basically. You want some kind of exponential mixing. So what that means is, for us, we need to develop a laminar chaotic mixer. So we have low energy, low shear rates, and the way in which we do this, and I'll describe this in just a minute, is we have flow reorientation. So we take a laminar flow, we run it for a certain amount of time, then we change the direction of that laminar flow. then we run it again, we change the direction. So that simple thing of just a simple linear shear is changed. But you can't just take any laminar flow and expect it going to mix. In actual fact, it's almost certainly not going to. So you somehow need to design in the chaos. This was started off about 40 years ago now by a guy called Hassan Aref, published a paper in Journal of Fluid Mechanics, and it was this flow that he called a blinking vortex flow. So we have one vortex at point A, one vortex at point B. We turn on the vortex at point A for a certain amount of time. We then turn it off and turn on the one at point B. Run it for a little while, go back to A. And so we just swap between the vortex flow generated at A and B. And this is an animation that was done of that particular flow. It's a computational result. And we can see that we're starting to get reasonable mixing. Here's an equivalent companion experiment. Yeah, absolutely. And we can see the experiment is pretty closely matching up with what the simulation is there. So, you know, we're on the right path. The thing about the blinking vortex flow is it's in an infinite domain, at least the theoretical solution. Infinite domains aren't very good for practical applications. And I should say, working in CSIRO, practical applications is what everything was always about for us. Okay, so how do we implement this in practice? And this is where Guy's brilliant idea came in. So he got this flow which was connected. So at the moment we're just looking at a 2D flow. We're going to extend it to 3D in a minute. So it's the flow in a disk. It's got a solid boundary, so the fluid sticks to the boundary. And we have this little aperture cut in here, and we move this bit of the boundary permanently. Now, how you actually do this is not obvious yet. It will become obvious in a minute. It's a little bit like the lid-driven cavity flow, for those of you who know that flow, but in a circular domain. The patterns that we see there are the streamline patterns. So we operate this flow for a little while. We then shift where this little moving window is. So we turn the first one off, we turn this second one on. Same streamline patterns, they're just rotated. Then move it to another place. Exactly the same thing. And we just keep on doing this continuously. But this again is a 2D flow. We need a 3D flow. And the obvious way of getting that is add a pipe flow. Put a pressure gradient into the page so that there's a flow going into the page. So we have a 3D flow, and schematically this is what we have. So we have an inside pipe, which is stationary. It has some holes or apertures cut into it, and they're offset from each other. And as the flow goes down the pipe, it sees one of these apertures, and then it moves a bit further down, it sees a different one. And so those streamline patterns are continually changing as the fluid moves down the pipe. And then it's wrapped by another cylinder, this outer cylinder, which rotates. And that's the thing that drives the fluid flow. It's the shear from that pipe rotating in each of these apertures here. Some parameters, I don't really have time to go into too much detail, but the aperture opening, how big do we make this aperture? The offset as we move down the pipe, how much angular change do we have for each aperture to aperture? And then this ratio of timescales. In other words, how fast are things moving down the pipe compared to how fast are we rotating the outside pipe? So those are the three key parameters. The thing is then, how do you actually figure out what a good set of parameters is? Because not everything is going to work. So we do spatial Poincaré sections. And for us what that means is here's our schematic of our device. It has a periodicity in this axial flow direction. We put in a few little particles up there, we track them down, and as soon as they hit this plane, we add a few dots to our plot, and then they hit this next plane, we add a few more, a few more, a few more, and so we build up this picture of the flow. Where do things mix and where do they not mix? And here's a set of examples for one particular case. So the axis going across the top here is the offset of the window, one from the next. And going down here is that time scale. In other words, how long do we let the fluid see one of these apertures before it moves on to the next one? And you can see that certainly all of these things here across on the right-hand side, we have all of these island-type structures. So inside each one of these structures, there is no mixing. So the fluid just might go round a little bit, but it just stays in a nice singular path. Likewise on the left-hand side here. So these are negative offsets and these are positive offsets, but you can see there's this region here where the mixing is pretty uniform and pretty good. So this then gives us a place as to where we want to start looking for designing a real one of these experiments, a real device based on this. And just to show you that if you choose the wrong parameters, you can get some pretty bad mixing. So here we have something that's half green and half red, and it goes and it goes and it goes, and there's a little bit of mixing between the green and the red, but there's huge regions that don't change. Whereas if we choose the parameters well, it's a very, very different picture. So you can't just use anything. You've got to be careful, you've got to be clever in the way that you actually design these things. Now, it actually turned out that this mixing on the right-hand side wasn't quite as good as we'd hoped. And those of you see carefully, we've got this little region here that actually doesn't mix. So we should have really adjusted the parameters a little bit more in this visualization, basically. So we have the theory, we got the concept, we actually built one of these things. Very practical. And we operated it, and I remember speaking to the group, or the program leader at the time, and I was saying, oh, we're going to do this experiment, we're going to put 2 dye streams in, it's going to mix really well, and then we're going to change the direction of rotation of the outer cylinder, and the red dye stream won't mix. And he looked at me and said, oh, you computational people, you always think you know all the answers, I'll bet it doesn't work. Anyway, this is the case where we had the 2 dye streams, and we can see as we move down the pipe in this direction here, the fluids mix. I mean, you can still see striations, but they're mixing reasonably well. You rotate exactly the same device at exactly the same speed, but in the opposite direction. The simulation predicts this big red region that doesn't mix, and so we put the red dye streak right in the middle of this, and you can actually see it, not so clear, it goes all the way through the mixer without doing anything.
You deprived him of his schadenfreude.
Oh, no, he ate humble pie, that was really good. Okay, so that's the basic pure, I guess, kinematic mixing. One of the other things that we might want to use a device like this for is for doing something, for example, like heat transfer. We might want to take a hot fluid and cool it down, or a cold fluid and heat it up. And so the problem, the mathematical problem for that is the advection diffusion equation, which is written in non-dimensional form there. So the velocity field U here transports our scalar, and scalar could be heat, it could be a dye, it could be a chemical. And it provides chaos independent of whatever phi is. And then diffusion, of course, smooths out the gradients. And Peclet number here is another system parameter. We have to worry about that because the results will depend on the Peclet number. The 2 questions are, can we optimize this? And I think what the most interesting is, does the optimal mixing also provide the optimal heat transfer? Which for me, I would have thought, yeah, of course it will. We're going to see some interesting results that proved me wrong. I'm not going to go through the details of this primarily because I've forgotten them all. And this is work that Dan Lester did, very good mathematician for a chemical engineer. If you expand the solution for our scalar in eigenfunctions of the advection diffusion operator, you get this series of terms and you truncate it somewhere. These eigenvalues here, so basically we've got a set of these eigenfunctions. They're multiplied by e to the lambda t, where lambda is a negative eigenvalue. So these are always decaying solutions. We never have to worry about things getting bigger. And provided the certain conditions are satisfied, the solution to this problem here converges to a dominant spatio-temporal pattern that decays in magnitude. And these things are called strange eigenmodes. And if you want to do a finite time solution, you actually only need a few modes, because most of these eigenvalues are sufficiently large or sufficiently negative that most of those eigenmodes decay very quickly. And in actual fact, for slightly longer term, you only ever need to really look at the first one. And so here's an example of a strange eigenmode. So red represents hot, blue represents cold. We're trying to cool this down. On the right-hand side here, we have the magnitudes of the 2 different shapes of the 2 different eigenvalues, and we see very rapidly there's almost no difference between the full solution and our first eigenmode. So provided we know what the eigenvalue is for this one, we can figure out how long it's going to take to do the heat transfer, basically. And if you do that for a whole ton of different parameters, which is what we did, Going across here, this horizontal axis is the angular offset of the window. The vertical axis up here, it's equivalent to that beta parameter I introduced previously. It's the time, how long we actually operate things. We get a plot that looks like this, where this is a contour map of the eigenvalue. It's actually negative of the eigenvalue. So red means it decays quickly, so the heat transfer is good, and blue and purple down here means it decays really slowly and the heat transfer is not so good. And so we can see on these things here called Arnold tongues, they're fractally distributed, and they're on ratios of integers. That's where all those things happen. And on these so-called tongues we get mode locking. I'll show you what that means in just a minute. The best mixing for this particular set of parameters occurred roughly up there. But I think you can see from this, the best heat transfer occurs nowhere near that. So different values, or one similar value of theta and one very different value of theta, but very, very different values of the time scale. So this was a really surprising result. Knowing that you got good mixing doesn't mean that you're necessarily going to get good heat transfer, chemical diffusion, whatever else.
That's weird.
It is super weird. It is absolutely super weird.
Do you understand?
Yep. So on those tongues we get these ordered solutions. So we get this so-called mode locking. So around one of these tongues here, let's just choose that one there, we get the eigenfunction that looks like this. So what we've got is we've got very steep gradients in temperature very close to the wall. So that means you get better heat transfer. Whereas if it was just, a cylindrical pattern, you get much, much slower heat transfer because the gradients would be much less. And so these are just some ordered solutions on the tongues there. The best mixing is not equal to the best heat transfer, which I still think is a pretty amazing result. In terms of how well it works, for a Peckley number of 10 to the 4, which is one of the ones we looked at, it's about 20 times better, which is good. So this started off with mathematics and this simple idea of the blinking vortex and how to implement that in practice. We went through various iterations of developing this. We actually got a commercial partner for a while when I was at CSIRO. They installed one in a very well-known food manufacturing company. It did the mixing of their product about 20 times better than their current technology, and they decided not to go ahead with it.
Why?
I don't know. I'd left CSIRO by then, so I'm not sure. I wasn't privy to the details. No, they just didn't want to go ahead with it. No, I'm not going to tell you. I cannot possibly tell you what it was. So anyway, that's my story. I think it's actually quite beautiful, some of the things that we did there, and it's also quite practical. And I think that these two things together, I think, it was absolutely fabulous. So I hope I nailed your brief there, Rosemary.